A blockchain is a ledger that is immutable. Okay, let's back up and try again. First, and most important, a blockchain is a ledger. A ledger is a list of transactions. You use ledgers all the time. If you log into your bank's website and view your account or credit card activity, you'll see a list of transactions, ATM withdrawals, deposits, payments, and so on. The list of transactions is a ledger. That ledger is immutable, which means it can't be changed. For example, if you find a charge that was in error, the bank can't actually remove the charge. What they do instead is create a new transaction that refunds your money. Enterprises use ledgers for all kinds of things. Financial records, of course, but also scenarios where a permanent record is important. Deals, support case comments, licenses, registrations. Any case where you want a permanent sequential recording of transactions can be implemented with a ledger. A blockchain is a particular way to implement a ledger using software. That's it. That's all it is. So what is that particular technique that makes blockchain special? In a regular ledger, each entry in the ledger is independent. If someone modifies one entry, it has no impact on any of the other entries. But in a blockchain, if someone modifies one entry, it instantly invalidates all of the subsequent entries. In other words, blockchain makes it harder to tamper with ledger transactions and easier to detect tampering should it occur. In order to accomplish this, it uses something called a hash. A hash is a value that is produced by a hashing function. A hashing function does the following. It takes in any data you wish, it processes it, and produces a value. A given input will always have the same hash value. Even a tiny change in the input can result in a dramatically different and unpredictable hash value, and it's impossible to figure out the input given a hash value. In other words, it's a one-way function. Let's see what happens if you add a hash value to each entry in the ledger. If someone were to change the transaction value, it would no longer match the hash. The only way someone could tamper with the transaction would be to also recalculate the hash. If they didn't, you'd be able to spot the tampering. Still, calculating a hash is pretty easy, so not much has really changed yet. What happens if when you calculate the hash, you include not just the value of the transaction, but a hash of the previous block? Now things get interesting. If someone tampers with the value of a transaction, they can recalculate the hash value for the block, but that hash value is used in the next block, so the hash value stored in the block is no longer correct. Even though the next block hasn't been modified at all, it will detect the tampering on the previous block. The blocks have been chained together, hence blockchain. In fact, it's the nature of a blockchain that in order to tamper with any block, you have to modify all of the subsequent blocks. If you can make that modification either very hard to do or easily detectable, or both, you will have in effect an immutable ledger. In the next couple of clips, you'll learn more about how that can be accomplished. But before that, let me point out one interesting aspect of the blockchain. Because the hash values are based on the transaction data and the blocks are chained together, if you know for sure the hash value of the most recent block, then you can prove absolutely whether or not the ledger has been tampered with in any way, because even the tiniest change in any transaction would result in a different hash value on the most recent block. So making a blockchain ledger immutable has two possible components. Making it hard to modify the blockchain prevents tampering. Making it hard to lie about the hash value of the last block makes it easy to detect tampering. I want you to really think about those two concepts because they are the drivers of the technologies you are about to see and will ultimately drive the design approach you'll see in the next module.